main part of the course starts. So we'll learn how to design from the basic steps, okay? So three parts, again, like last couple of days. We start with the how to find the sizing of the machine analytically first. Then we'll look at what are the limits and constraints to determine the size and the various quantities. And last part we'll be looking at why we will need finite element and what does finite element, how does it do, okay? So today that will be the main content, and tomorrow we'll be looking at, today the design that we develop will be a base design. So how do you optimize that design? That we'll be looking at tomorrow. And then half part for tomorrow will be also starting of the controls, okay? And then the next day will be control. So how to size and design motors for EV traction? I guess that was the main motivation for most of you to do this course. So this hopefully will answer this question today. And in the first half, our goal is to identify the fundamental aspect, how to design the machine. Then the key equation that we use for designing this machine is called sizing, classic sizing equation. So we'll be looking at where this sizing equation comes from and how to use it. And then we'll try to determine the dimensions, main dimensions, okay? So the first step, when you are asked to design a machine, the first step is always in your application for what you are designing it for. In this case, in our case, it's traction, right? And we learn how to calculate the traction force. So from traction force, we will be able to determine what is the required rated power, okay? And the vehicle that the design you are doing, the vehicle will let us know what is the speed it requires, okay? Let's say in first gear it want to accelerate up to 10 or 20 kilometer per hour, okay? So that will determine our base or rated speed, okay? And then we can decide what type of machine we want to use for this application. As we said, it could be permanent magnet, but it could also be other types. So you decide at this point what is your choice of machine, okay? Although the discussion is about PMSM, but this equation that we are going to develop can be used for any type of machine, okay? After that, you can determine your phases, 3-phase, or you want to go for more than 3-phase. Then you can decide on what type of construction you want. Do you want the internal rotor, external rotor, internal or external pole? Do you want axial flux? Because let's say your application is not traction but wheel motor, then maybe you will prefer to use axial flux motion rather than radial flux. So at this point you can decide what type of construction you will be going for. And the rated speed that we have found from the vehicle's minimum speed will also help us to determine the poles, how many poles we will want in our machine, what will be the frequency for that machine, okay? And the battery voltage is going to tell us what's the rated voltage we will have for the machine. And then we can decide what we want to optimize this machine for. Do we want high efficiency, low cost, reduced ripple? And if we want to go for sensorless control, do you want certain type of saliency? All that sort of things you can determine. But in first stage, it may not always be the most necessary uh, parameters what you want to optimize in first step. You may not need to determine, okay, but it could be your goal. Then in the next step, it will be your goal, okay. Similarly, the enclosure, whether you want, what type of cooling, all those can be determined at this stage or could be later. Similarly, the compliance with standard, etc. Okay. Cost and manufacturability is usually should be considered at the first stage, because if once you have designed it and you found that you can't construct, then that will be an issue, right? So we must be aware of uh, that it can be manufactured easily, and we must have certain cost assigned to it. If you are working in industry, actually industry may already give you some indication of how much cost they are expecting, okay, for per piece of motor. So cost could be part of your optimization process, minimizing cost and maximizing something, okay. So and that's also should be at least have some idea. And if you are in research area and you are just doing prototype, then cost may not be an issue, because that time still you have some limit, but you may not need to optimize the cost. So these are the parameters you determine first, and then our actual work starts, right? As I said, we'll start with for traction application, we start with this equation that we discussed in our first lecture, right? And we can calculate out these forces, already know how to do that, if we know the mass of the vehicle especially. And usually, when we calculate the rated power, we only need to consider the rolling resistance and the air drag force. Okay, these two force, summation of these two force, in fact, is equal to your rated power of the motor. Okay, and when we consider the other two as well, along with the first two, this gives you actually your peak power, okay, when we consider all four. So peak power is required for short time, okay, only during acceleration. You will need the acceleration power. This is inertia or acceleration. This disappears once once your car settles at a particular speed, okay. So while driving, this force is not there. Gravitational force, that means just force related to slope angle, it only comes when you are driving on a hilly road, right? Accelerating on a hilly road. So again, you don't need that for full like normal driving in a flat road. So that's why the other two or all four gives you the peak power, but the first two is the main one, which determines your rated power. So we calculate rated power. We know the force, and from the force we calculate out first the torque on the wheel, because this force, this traction force that we calculate is only on the wheel, okay? So first we have to calculate what is the torque on the wheel, and we will always have a gear, okay? There will be a reducer in your powertrain, more than likely, okay? Very rarely it will be direct drive. So the gear ratio will tell us what is the torque on the motor, okay? First you find torque on the wheel, and then with the gear ratio we find what's the torque on the motor. And speed, similarly, the vehicle speed requirement and wheels radius gives us the speed of the wheel, the rotational speed of the wheel. And again, with the gear ratio, we can find what is the rated speed of the motor. Okay? So traction force calculation, and from there we find out the torque, power, and speed and their relation. So torque of the motor and the speed of the motor gives us the power of the motor. Okay, so we calculate out the required power. This is the rated power. Okay, or we can also calculate peak power, but usually you start with the peak power. Now, once we have the peak power or rated power calculated, next we need to determine the dimension size, the base design, basically. So for that, we have to look at our geometry, right? Now, we could go for SPM if it is some with concentrated winding. SPM can be used for traction as well because it has flux weakening. Or we can go for IPM, which is much more common. Components we have, the main components. So first, for dimension, you may want to know what is the diameter, right? What is the diameter in this 3D picture? This is your outer diameter, and up to here, up to the air gap of the stator, or maybe you can see here better. This is called air gap diameter. Okay, I'm showing it as a radius, but you can consider it as a diameter as well. Okay, so if we consider this as a diameter from center to the inner diameter of the stator, that is also referred as air gap diameter, dz. Okay, we'll be using this variable here. And the length, the axial length. What's the axial length here? LE. So these two are the main dimensional parameter we need to determine, which will tell us what is the size. Okay. Once we know dz, we can also find what is the outer diameter. Okay, because sometimes there are some ratios. Particular ratios are there, need to be maintained, and so we know dz, we can find out d out as well. Okay, so sizing's equation that we're going to discuss basically tries to develop this equation in terms of dz and le, axial length and air gap diameter. Same thing for any machine. Okay, at this point we haven't decided whether it will be IPM, SPM, it doesn't matter at this stage, okay? So to go to that equation which will give us these dimensions, there are a few more dimensional parameters we will need. Here you are seeing it is for SPM, but IPM, the stator part is same. So apart from that, the air gap diameter and length, we may want to know what is the slot's dimension, the depth of the slot, width of the slot. We may also want to determine the permanent magnet's size, okay? The width here, this is the LM parameter that we discussed last time, okay? And the this is the for surface time, that's your LM basically, and for IPM it's again same. This will be your LM, okay, which is the main parameter. This part is, we can say, as a width of the magnet, so that even though it affects your cross-sectional area, but main effect actually comes from LM, okay, width of the magnet. So all other these parameters actually depends on your outer diameter and your air gap diameter, okay, and it will also depends on how many slots we have, okay, and how do we determine slot, that we'll talk later. But you can see the main dimensional parameters that we will need once we determine the other two, dz and le. So next slides we'll be discussing the equation that we're going to use to calculate dz and le. Okay. So it comes from the base, it's called classic sizing equation. Okay, so you may see it looks like a very complex something, but as we go deeper into this equation, you'll find that everything will make sense to you. Okay, and this equation was developed by Professor Lipo, I think. Yeah, so here you can see the paper which actually described this equation. The paper was by Professor T.A. Lipo, and in 1998. And this equation was actually developed as a general machine design equation. So this equation can be used for any type of machine. That was their goal. So if you want to learn more about it, you can read that paper. Okay. So you can see that first it was developed as a power equation, but it can also be used as a torque equation. Okay, so because power divided by speed is your torque, the advantage of using torque is that if you compare this equation with this, you know that in the torque equation we don't have force frequency over pole pair component. Okay, sometimes in your design you may want to optimize number of pole pairs. You may want to optimize frequency. So for those type of application, you may not know initially what is your number of poles, what is the frequency going to be. So in that case, you can start with the torque equation. Okay, only difference is that frequency and pole pair is not there in your torque equation. So how do you get this equation, and what is all this parameter means? It in fact starts with a very basic equation. It's the average power equation, if you remember. Okay, for AC system, average power is calculated as instantaneous voltage times instantaneous current in one time period. Okay, so that's your average power equation actually. T is the time period. M is number of phases in your machine, and eta is the efficiency, because we are looking at output power. So we multiply the average instantaneous input power by the efficiency. And in the equation, in the basic equation that we know from our circuit is actually the voltage, terminal voltage, Vt, It. But here we use EMF, back EMF, ET time IT, okay? So we ignore, as we know from our last discussion, the terminal phase voltage is back EMF plus current time resistance time L di dt, Ls in case of synchronous machine. So we ignore this and we ignore this. And so we just consider V, input voltage is equal to our back EMF, okay, in this equation. So we do it E time I as our instantaneous input power. And as I said, this equation was developed for any machine, so we don't assume anything at that point, at this point, except for we are ignoring resistance and inductance. And efficiency, we may assume at this point something, let's say I1 95% or I1 98%. So we can assume efficiency that we are aiming to get. Now, if we do this integration, obviously time period will cancel out in our integration, and we will end up having the peak value of the back EMF time peak value of the current multiplied by a factor Kp. So what this factor is this factor can be determined outside of this integration actually. Although by maths it will be same as what we are getting here, but we can do it outside. And as well. So Kp is actually nothing but your average instantaneous power over peak power, the ratio of those two, okay? If it is a sinusoidal voltage and current, it is quite a well-known factor, okay? It's simply your average instantaneous power is RMS, VRMS, IRMS power factor, right? Cos phi. So in this case, it's same, ERMS, IRMS, cos theta, but this theta is the angle between back EMF and current, okay? Back EMF and current. So ERMS, if you are doing a SPM machine, or if you consider ID is equal to 0, then in fact your current IRMS is also in phase with it, especially in SPM machine under maximum power torque per ampere control. We align current and back EMF. So your theta here is actually 0. In case of IPM, it is usually not 0. So your current is somewhere here. So this angle theta is not 0, but usually equal to a current angle that we define in our control, gamma, some gamma. That's how we define this angle, okay? Current angle. So theta could be 0, or it could be some angle based on our motor types. And as long as it's sinusoid, so this root 2, E peak is root 2 of root 2 multiplied by RMS value. So those two together gives us this factor half. Okay, so half time cos of the angle between E and I is the factor referred as EMF factor, or power waveform factor, okay, Kp. So for sinusoidal waveform, that's what it is, half cos theta. But if you have another type of motor where your back EMF is not sinusoidal or current is not sinusoidal, let's say BLDC motor, you will have a square waveform and a trapezoidal waveform, then Kp could be different, okay? Then Kp may not be half cos theta, okay? So that's what we need to remember. But for PMSM, it is simply half cos theta, okay? Or for induction machine also, it is half cos theta, okay? So any three-phase sinusoidal machine, it will be half cos theta. So Kp we know now from our equation here. This factor is known now, okay? This factor is known now. Next, let's go to the other factors. Now this back EMF, EM, the peak value of back EMF, it comes from very basic Faraday's equation. If we remember, the back induced EMF of the RMS value or peak value of induced EMF, in this case peak value of induced EMF by Faraday's law is equal to omega times the flux, right? EM is equal to peak of the flux. So this flux is in fact the flux per pole, okay? This flux is actually flux per pole. So we can write this in this form, okay? In this form. How? Let's look at it. So omega is 2 pi f, right? So that's what we are getting here, 2 pi f. Omega is just expanded as 2 pi f. And we also, if we have more than one turn, so we multiply this also by number of turns, right? By Faraday's equation. So that in our machine, obviously, we'll have more than one time. So that's your number of turns in your phase, okay? And phase comes from there. And then remaining is pole pair BZ and TZLE, right? This part. These two. So where it is coming from, you can quite easily understand. It's actually flux, right? Flux per pole, okay? Flux density time area or pole area is your BZ time area over DZ time LE. So it is obviously DZ time LE is a simplified area, okay? Simplified area. So you consider as if the stator is like a kind of like a rectangle, okay? So LE is your axial length and DZ was the diameter up to here. So it is the air gap, area of the air gap, basically, okay, per pole. So we divide it by pole pairs, PP. And in this equation, you may also, may note that we have also a winding factor. So in the machine, number of turns are distributed in the slots. So we will have a winding factor, right? So that's KW is your winding factor. So we have one additional factor there, number of turns. In this equation also, we could put a KW here. KW is your winding factor, okay? So now 2 pi times KW is definitely a constant, right? It's going to be a constant. So this 2 pi KW is actually expressed as EMF constant, EMF coefficient in this equation. So KE is 2 pi time winding factor. Again, you will be able to calculate out. Okay, winding factor we can calculate out if we know what is our distribution factor, pitch factor, or skew factor, if we have skew. So this pitch factor and skew factor may or may not be equal to 1 based on whether we have skew or whether we have short pitch in our winding. Okay, we'll discuss this a bit, how to calculate them, but just be at this point, just know that we can't calculate KW, winding factor. So now, if we look at that, this part of the equation, you note that this is the contribution of magnet, okay, because it's EMF, remember? So, and this EMF is coming from when the magnets are rotating. So, and this flux BZ is the air gap flux density of, peak air gap flux density coming from your magnet. So BZ, that's why is also referred as magnetic loading of your machine. Okay? So BZ, air gap flux density, that's why when some of you may be doing finite element type of work. So when you do a machine analysis, first thing usually you always look at is what is this air gap flux density. Okay? You do a finite element design, check what is your air gap flux density, the waveform. You may find the waveform and then you can do a Fourier analysis to find the peak, the fundamental peak. Okay, so this BZ will always can be found from finite element, and that's what we should do always as a first step. But at this stage, we still do not know our geometry, so we haven't gone to finite element yet. So at this point, the BZ, we can simply estimate or assume rather, okay, what will be my typical BZ? What is the typical BZ I'm expecting? Maybe I expect it to be 0.8, maybe I expect it to be 0.85 or something, so around that value. So this is, I may assume at this point as, let's say, 0.8, okay? And other things, number of turns and the winding factor, I can calculate or I can determine, okay, based on my requirement. In fact, if you remember that if we know our rated voltage, we in fact know what is going to be EM, okay? What is the value of EM? We actually can estimate because EM will be approximately equal to our peak value of our rated voltage, right? Approximately. So if we already decided what is our rated voltage for the motor, we in fact also know what is our EM at that speed, at the rated speed, okay? So if EM is known, we can again estimate from there as well the number of turns. After we know what is BZ, we determine what is winding factor analytically, and we can determine what will be our number of turns per phase. Okay, so turns phase can also be found at this stage. So BG will be known, number of turns can be calculated, and KE can be calculated once we know winding factor. And the frequency and volt pair we may or may not decide at this point. If we are using torque equation, then we don't even need this parameter. And if we already decided our pole pair and frequency, then we use this power equation and we will know this ratio. Okay, so everything here is kind of known at the moment, right? For the EMF part. Then we go to the next part is your current, right? So if you look at the back of all our parameters, you may note that I haven't decided the current yet. Okay, I have decided voltage because voltage will come from my battery, so I know what is the battery voltage, so I can calculate out what will be my rated voltage for the motor. But I don't know my current because I don't know my torque yet, right? Or I know a rough idea of torque, but I don't know what the current going to be. Okay, so next part is to looking at the current. So how do we decide current? Again, the peak value of the current usually is this. If it's a sinusoid, it is RMS value of the current time √2, right? But in the sizing equation, they haven't decided that the current is always going to be sinusoid. So that's why they use a factor and call it current waveform factor, Ki. Okay? But for if it's sinusoid, we already know what is Ki. Ki is simply √2. Okay? But if it is a square waveform, then you have to calculate out what is Ki for a square waveform. It will be 2 by 2 over pi, I think. Something like that, okay? For different waveform, Ki will be different. So Ki will be known, and IRMS, current, actually the current doesn't help us much. We are more interested in how much current density, because we are dealing with geometry at the moment, right? So it's much more important to know the density of current rather than the total current, okay? So that's why we could find out what is the current per meter, okay? Current per meter, and defined here as AS, or it's sometimes called electrical loading, because this is the parameter which relates to your current, okay? Or electric field, basically, okay? Out of electromagnetism, this is the electric field, okay? So it's called electrical loading. It's actually nothing but total current per meter. So how do we find current per meter? I have IRMS, and I multiply, this is the current flowing through each of your conductors, right? So you may have number of turns, okay? So 2 conductors form 1 turn, right? This is a turn we define. So two sides of the conductors together gives you a turn. So that means number of turns multiplied by 2 gives us total number of conductors, okay? And we may have more than 1 stator, okay? Some machines have double stator, some machines have even like for more than 2, okay? So if you have more than 1 stator, you need to consider number of phases of each stator. For example, you may have a 6-phase machine. 6-phase machine, but 3 phases in one stator and 3 phases in other stator. It could be like that. And then it will be M1 will be total 6 phases, okay, and so on. So number of phases of each stator. If you have 1 stator, it is simply 3, okay, 3 phase, okay. And so that is the number of turns, phase, multiplied by current gives us the total amount of current in your machine, right? Divide this current by the length to get ampere per meter. So length is nothing but the perimeter of the air gap. Okay, so that means pi times d. Okay, so this pi times d is the total length of the conductors, because the conductors are wrapped around, right? So that if you open it up and put it like a circle, it will be, you will get this pi times dz as your length of the total length of the conductor. So total current divided by total length gives us this stator current loading. Okay? And some machines might have also rotor loading, for example, induction machine or current excited synchronous machine. We will have also current in the rotor. So if we have current in the rotor, we should also consider rotor current loading. So total current electrical loading is in those type of machines is summation of the stator current loading plus the rotor current loading. So you may not calculate the rotor current loading if we can determine a ratio between the stator and rotor current loading. Okay, so this ratio is K phi. And then the stator current loading can be expressed as a function of the total current loading over this ratio, 1 plus over this ratio. So from this relation and this equation, we can find what is the relation between stator current loading, total current loading. Okay? And so for in general, that means the current Im can be expressed as Ki, the current factor, current waveform factor, As in terms of total current loading, and the factor K phi multiplied by the length and phase and turns. Okay. So for PM machine, obviously we don't have rotor loading, so K phi is going to be 0 for us. Okay, for PMSM, K phi is simply 0, and stator current loading is the total current loading. Okay, so in the PM machine, this becomes simply 0, and this becomes A equal to AS. Okay, so again, in the now if we combine the EMF part and the current part, you can now see all the factors. We have this, you can calculate each one of these factors now. Okay? And if you have three-phase machines, and this simply becomes equal to M. Equal to 3. Okay? M over M1, it becomes simply equal to 3. If using power equation, you will know frequency and pole pairs. And this is your current loading, this is your magnetic loading, and dz squared, because now we have a dz here and a dz here, so it becomes dz squared, the air gap diameter squared, time Le. Okay, Le is the axial length. All right. So two unknown for us, dz and Le. We said, okay, we may estimate what is BZ, or we may assume what is going to be our BZ. That we say 0.8, let's say. Now A, value of A, also we can use some typical value of A at this stage. If we, because our main intention is to find what should be DZ and what should be LE. Okay, so we may also assume a value for electric loading, a typical value of electric loading for a typical power. Okay, for here you are seeing some typical values used in conventional machines. Okay, for 1 horsepower, electrical loading is 11.5 ampere per millimeter. Okay, and so on. So this can be, you can find it for conventional machines. Okay, even you can find for PMSM machines. So at this stage, you can just assume one of those typical value based on your calculated power. Okay, so we mostly will know what is A and what is BZ at this point. All other factors can be calculated. So only unknown is dz square and LE. Okay, and that's your active volume of the machine actually. It's also called active volume, dz squared time LE. This is simply showing you what those factors if we have a PMSM, okay? And you may note that all this can be calculated. Ke was equal to 2 pi omega, k omega, k omega. So, and k omega is the winding factor. So everything in this blue colored part will be known. A and B, Z, we can assume some typical value at this point. So only unknown is dz square and LE. So next, but we only have one equation. So out of this one equation, we need to now estimate the two unknowns, dz and LE, right? One thing we could do is we may decide what is the aspect ratio of our machine. Aspect ratio is the ratio between the axial length and the diameter. Okay, so there are again typical aspect ratios for machines, okay, PMSM machines. So we may assume such a typical value. And in that case, the whole equation, if we substitute LE as KL times DZ, my equation becomes only unknown is DZ cube. Okay? Or sometimes what we may know is if we know what is the frame size of the motor, okay? If we know the frame size of the motor, the outer diameter will be known, the outer diameter, not dz, but the outer diameter, okay? So if outer diameter is known and there may be defined ratio between outer diameter and air gap diameter, okay? This is for some typical frame size, okay? And then you can again write the equation in terms of outer diameter and this known ratio, or our whole thing could be in the terms of outer diameter, and then you find out, oh sorry, in that case you may note already what is dz from this ratio, okay? You find that d out is known. So that's how you can find out the two main dimensions, okay? And this is what you should do as your first stage. If you're doing it from scratch, you have no other reference point, then this is where you should start. And sometimes, especially those who are working in industry, there may be this, your customer may just simply give you a area where you need to feed the motor in, okay? Certain volume, okay? And they say that they want, let's say they want a 200 kilowatt motor in a, I don't know, 2 meter square or 2 meter cube of volume, okay? And asking you whether you can design it. So in that case, you should not say yes. Rather, you use this equation to estimate whether a 200 kilowatt motor can be fit into that volume or not, okay? And if you see that, oh, that's not possible, you then mention that it may not be possible because the very conventional, the basic estimation is showing me it will be impossible to fit into this area or this volume, okay? So before you say yes, always put some conditions if you are doing it for some industrial customers, because they don't know the physics, right? They just have certain requirement and tell you to design things. And this equation is really good way to check whether it can be really done or not, okay? And all of these parameters can be found easily. So this is our first point. Next is those factors. So this part we can go quicker because this is again conventional factors determination. So we usually in three-phase machine, distributed winding, there are two types, lap winding or wave winding. And for PMSM, mostly lap winding is used, okay? And what does winding means? You should just remember that winding is actually connection of several coils, okay? And coils are formed through the turns, okay? So even though it's basics, you should remember, okay? Sometimes we just forget what is winding. Winding is actually a lot of coils, okay? And those coils need to be fit into your slots, okay? Your slots, okay? And these windings we must distribute in a particular way so that we get 120 phase difference between each phase windings. Okay, you cannot randomly put like phase windings in random slots. It has to be in a particular way so that we get 120-degree phase difference. Okay, so for example here, if we have, let's say in this case, I think we have two-pole machine. This is a two-pole pair machine and three-phase, very simple one. And you note that, so that means there are 4 poles, okay? Two-pole pairs, 4 poles. So you can see there are 4 zones, okay? Each zone under one pole. And note how each phase is need to be, okay? So phase 1A, here it is phase U, is positive, but second phase W is negative, and the third phase C or V is positive. So it has to be like this, okay? Under one pole. If we don't have this, you will not get 120 phase difference between the 3 windings. So that's how we have to distribute. We may discuss a bit more there. And the second thing is slots. How do we decide how many slots we have? We must have, okay? And slot per pole per phase. How many slot per pole per phase? Also short form SPP is a very important parameter actually, okay? And slot per pole per phase, if it is an integer number, then it is, we call the conventional distributed winding integer slot machines. If this factor is fraction less than 1, then we have the fractional slot type windings, okay? Fractional slot could be even distributed winding, also could be fractional slot, okay? Concentrated winding is always fractional slot, especially if it is used as a PMSM. But if it is like distributed winding, fractional slot is common in the hydro turbine, generators with hydro turbine. Okay, they often has fractional slot distributed winding because they have large number of poles and they cannot have enough slots, so they end up having fractional slot distributed winding. Now this factor, larger this factor, so usually for conventional distributed winding it is between 2 to 10, okay? And larger this value, better is your magnetomotive force waveform, MMF waveform, okay? And closer the MMF to sinusoid, you should have better torque ripple, okay? Because your torque ripple comes from the harmonics of MMF and harmonics of flux density, okay? Together, interaction of those two gives you the torque ripple. So more sinusoidal MMF should have better torque ripple, okay? So that means larger this factor Q for integer slot machines, better is its torque ripple performance, okay? So you can see here when Q is equal to 1 and when Q is equal to 3, the MMF waveform, okay? The red one is when Q is equal to 3. compared to when Q is equal to 1. So you can see how the red one is more closer to sinusoids, right, compared to the blue one. And you can also see the harmonic distribution here. So the blue one has larger harmonics, larger higher order harmonics. Okay, and these harmonics is going to give you the torque ripple. Okay, so Q is a good, like a important parameter, and which actually decides what should be your number of slots in your machine. Okay, and another thing is that we have some limitations here. So if you have usually you have at least 2 parallel paths in a machine. So you, depending on how many parallel paths you have in your circuit and number of phase, this slot over phase over parallel path also always must be an integer. Okay, and that in fact determines how many coils you will have in each phase. Okay, so coil number is also not random. It actually comes from how you are distributing it, and this must be a constant, otherwise you cannot distribute it uniformly. Okay, here you can see this is actually coming from JMAG, the software. They have a very good tutorial of winding distribution. So if some of you are finding it challenging, please feel free to go and look at their website. I think it was done by Professor T.J. Miller. So Professor Miller's materials are there. Feel free to look at them to understand the winding distribution better. Okay. This is just showing you, they may have many more figures. I just picked one figure here just to show you how the coils are distributed for one phase. For this particular distribution, there are, you can see, this is phase A. Okay, this is phase A. And in phase A, they have 1, 2, 3, 4 coils. Okay, and you can see how these coils are distributed. So first coil is, so in this machine, 3 slots per phase. Okay, so one phase requires 3 slots to distribute. So one coil is in these 3 slots here. The second coils is done in a different way, you can see. Okay, so there could be some implication how they are connected. So coil number, second coil is in the connected as coil 1 and coil 4 is connected as something's a bit different way. This is because this all things comes from your, you know this rule, right? How the flux density and current. So from there actually it comes how they are connecting it. Okay, sometimes to make the flux adding or induced EMF adding to each other, they have to connect like this. Okay, if you connect other way, then this EMF induced in coil number 4 may be deductive. Okay, so that all the EMF are summative, additive, summation of all the you may need to connect a bit differently sometimes. Okay, so that you have to, means it comes from some experience, but you can look at this material. Okay, and other thing is in the case of concentrated winding, we mentioned this. So concentrated winding, compare the concentrated winding and distributed winding here, these two pictures. Both of these windings, slot per phase is 2, right? The red color one, you can see both cases slot per phase is 2, but for concentrated winding it is so simple. Okay, and it requires much less number of slots. Okay, so construction is easier, that's why for concentrated winding. However, your MMF is never going to be sinusoidal. Okay, you will have higher order harmonics in your MMF for concentrated winding. But for concentrated winding, if we have a particular slot per phase per pole, SPP, we could have actually sinusoidal EMF. Even though MMF is non-sinusoidal, EMF becomes sinusoidal, which help you to reduce torque ripple, as well as you could end up having a better performance. But this is only for certain slot per pole combinations. So you cannot have random slot per pole combinations in concentrated winding. Okay, there are particular combinations you have to use. If we go through those, then we can have sinusoidal induced EMF, and we can have much smaller torque ripple in this type of machine because your EMF becomes sinusoidal. And other one is because you have high harmonics in your MMF, so it can increase the LD inductance. And that's why, as I mentioned previously, this ratio lambda PM over LD, known as characteristic current, can be made equal to rated current. And because of that, SPM machine also could have flux weakening or wide constant power speed range, only if this condition is satisfied. Okay, and that can be achieved only by concentrated winding. So if you want to use SPM and want to have a wider flux weakening or CPSR, this is an option, going for concentrated fractional slot concentrated winding. But because you have higher MMF harmonics, so you may end up having larger eddy current loss, both in your rotor as well as in your magnets. Okay, so that's your compromise. If you are willing to compromise with magnet temperature, but you will have certain cooling for your magnet, and you do not care too much about this eddy current loss, then but you want to go for SPM, this is the option. Okay. So this is simply showing you different type of SPP. First one is a integer slot distributed winding, SPP is 2. Second one is a 6-pole, 4-pole concentrated winding, SPP is half fraction. 6-pole, 4-pole, SPP is half fraction. Okay. Then another is, remember the slots, we have limited space to put all our copper. So we may want to utilize the slot space much more effectively. And how do you do that? Instead of putting only one single coil side in the slot, we could put two coils, two separate coils. Okay. So if we have two separate coil side in one slot, we have that double layer type windings. Okay, single layer and double layer. So this is a single layer structure, which is compared here with a double layer structure. Okay, the advantage of single layer is, especially if it's a concentrated winding, there will be very, very little mutual inductance between phases. Okay, so your fault tolerance is much better. Okay, if your application is about fault tolerance, then you want to use concentrated winding, then you should use single layer. Okay, but the single layer has this problem because of higher MMF harmonic, higher than the double layer, so you may end up having higher eddy current loss. Whereas double layer, although the mutual inductance will be a little bit higher compared to single layer, but it can have better MMF harmonics, and that's why can have lower eddy current, as well as you will be utilizing the slots more effectively. Okay, so both being proposed, but if fault tolerance is not the higher, not the requirement, then or not the critical requirement, then usually double layer windings are preferred. Okay. Here you are seeing, I think this slide we could have shown, I think before. This is simply showing you that what we talk about. Remember that your winding coils are must distribute in a particular way to get that 120 phase difference, right? This slide is actually showing you with a very simple integer slot machine. Okay, so let's look at the phase A, or phase 1 is in slot 1. Okay, there are total 6 slots we have in this. This is a very simple machine, so we have total 6 slots, and that means slot angle. Okay, we have 360 degree divided by 6 slots, so we have 60 degree slot angle, right? So A phase is in slot number 1, and B phase, we know B phase should lag A phase, right, by 120 degree, and C phase should lead A phase by 120 degree. So phase number 2, or B phase, is in slot number 3, you can see, so that we get 120 degree phase lag. Okay, that's why phase B is positive of the phase B is at slot number 3. Okay, and positive of the phase C is its slot number 5, so that you have 120 degree phase lead. Okay, so this is how you determine where the positive of each phase will be. Okay, it's shown for a simple one, but you can do it also for complex ones. Here you are seeing a laid out winding diagram, because if you want to have if you don't have a winding distribution winding already known, then you have to do yourself, right? If you're doing from scratch and you are not using a conventional distribution, then you have to do it from scratch. And in that case, usually laying out all the slots like a linear sort of things, although it is circular, assume you have open it up, and this is layout diagram for windings, and then we can determine where will be our positive of phase A, where will be our positive or phase B, where will be our negative, etc. quite easily, we can see. So you can see this is a 2-pole machine, so phase, and it has 2 slot, the first one, 2 slot per phase, okay, for this machine, 2 slot per phase per pole. So these 2 slots, this is, you have the positive end of A phase, this first 2 slot, and the negative end is the south pole, okay, of the same phase. When we have a connection like this is 180 degree phase difference, right, between the one side of the coil to the other side. So this, if we have 180 degree phase between the plus and the minus of your coil, it's called full pitch winding. Okay. However, usually full pitch winding again gives us a MMF waveform, not less sinusoidal. We end up having more MMF harmonic. So that's why then it's more conventional to use short pitch. Okay, what the short pitch mean is that it's no longer 180 degree, but less by 1 slot angle or something like that. Okay, so for example, this one is going this way actually. This one is going, going here. Okay, the other one may be going here. okay? And this one is going there, okay? So it is reduced by 1 slot. So it's a slot pitching by 1 slot, the second figure, okay? This third one is actually going to the pole coming from the other side, okay? If we have, or we can think of it's coming back and coming here, okay? Going all the round and coming here. The third, so this is, you can see, with the double layer, it's easy to do slot pitching, short pitching, okay? With single layer, you cannot do short pitching. If you are using a single layer winding, you will end up having full pitch only, okay? But with a double layer, we can also do short pitching easily. The third picture is showing same thing, but this time it was short pitch by 2 slots. Okay, the third figure. This is done for 2 slots. Okay. So if we have short pitching, we will definitely have a Kp, the pitch factor, not equal to 1 in our winding factor, okay? So we can calculate out this pitch factor from actually slot angles. This is again from the JMEG's materials. It is showing how a windings is distributed and how many poles, slots, etc. So feel free to look at it in your own time to understand how it is done, okay? And this is like it is actually, you may find this if you're using ANSYS. ANSYS provides you the conventional distribution of winding directly without, you don't even have to do it. You just need to define whether you want full pitching, short pitching, etc., and they will do it automatically. They have this, they have a additional program. It's called RM Expert, XPRT, I think. So this program is, it does most of this type of basic things, okay? They will users define things and it just distribute the windings for you, and it will give a picture like this, okay? You can also tell them what type of slot, because there are different design of slots. So you could have a slot like the one we have seen previously with a circular top. You could have a slot with a flat top like the one you are seeing here. So what type of slot you want can also be, you can tell RM Expert and it will design it for you. You just provide the dimensions, it does it for you. So it makes things very, very easy. You don't have to do it from scratch if you want to save time. But some other programs like JMEG or even TILA's, I think, Flux 2D, etc., they want you to do from scratch. And in that case, you just need to know the dimensions. If you are familiar with AutoCAD, then drawing the geometry is basically doing AutoCAD, okay? So, but then you have to distribute your windings also by yourself. And for that, that layout diagram is very, very handy, okay? You can define where will be your positive of your A phase, where will be your negative B phase, etc., okay? And this is actually just coming from classical textbook, how to calculate those winding factors, okay? Distribution factor is always present in a distributed winding, even even for concentrated winding, okay? So that's why our winding factor is never equal to 1. It's always less than 1. And you want to get as high as possible because it's your EMF is being reduced by this factor, right? Kw and phase omega phi, okay? So if it is equal to 1, you get the best from your magnets. But if it's never 1, because your windings are in the slots. Okay, so Kw is less than 1, but you want to have as high as possible. And you can see the empirical formula to calculate distribution factor depends on slot per pole per phase, SPP, and depends on your slot angle. Okay, so these two will determine how high your distribution factor could be. If it is pitch factor is present, then also it depends on your slot angle, basically gamma, and also the pole pitch. Okay, so this pitch factor is equal to 1 if you have full pitch. Okay, but if you have a short pitching, then this is not 1. You will have a value which you can calculate using a empirical formula like this. Third one is the skewing. So you may want to have skew in your windings or even in your magnets. Okay, if you have a skewing in the winding by certain angle, so you can see the skewing here. Okay, skewing of the magnets and the windings here in a 3D picture. So and it is skewed by certain angle. So this angle determines what is your skew factor. Okay, this angle. And again, it may not be equal to 1 when you have skewing, and that will affect your winding factor. Okay, so winding factor will be further reduced. But you may want to do skewing for reducing torque ripple. So it's a compromise, whether you want a higher winding factor or whether you want to improve torque ripple, okay, by doing a skewing. And once, if you remember, in the sizing equation, we ignored the resistance, right? So once we have determined the length of our machine, we know we have decided how many slots, we have decided what is going to be our current conductor size, we will be ready to calculate out the DC resistance. Okay, and it is coming from that simple fundamental equation that we discussed in last lecture or last talk. Okay, length, cross-sectional area, and conductivity of copper. Okay, but you were here the cross-sectional area of your conductor, and these conductors, all conductors are not series. There are parallel paths, so the resistance is will be become higher if you have more parallel paths. Okay, and you can also make it temperature dependent. As we know, resistance increases with temperature, so we could include the effect of temperature there while calculating. Okay, and you can, this is only DC resistance. So if you are concerned about high frequency AC resistance, then you should calculate also the AC resistance at this point. Okay, using the expression that we discussed last lecture. Okay, so using DC resistance formula and AC resistance formula, you should be able to estimate the total resistance you are expecting in the machine at this stage. And then there's some more things. So your windings, when we are distributing it, part of it is actually coming out. As you can see, this is your core area, right? This is the length of LE. But your windings has to come out and then go back to other slots. Okay, so this part is known as end turn. Okay, end turn actually does not contribute to your torque production, but it is there. You cannot avoid it because your windings are, your conductors are at different slots. So from bringing the conductor from one slot to other slot, it has to come out, right? So that end part is, the flux related to this end part is accounted for by inductance known as end turn leakage inductance. Finite element, if you are using two-dimensional finite element, it cannot account for this. So usually you have to calculate it out outside using an empirical formula like this, as was shown here, and add it to your inductance, calculated inductance. Okay? So this is an empirical formula for each coil. And total end turn inductance is in fact calculated from this coil inductance, end turn coil inductance. Okay, so once the slot dimensions are known, this can be calculated out. Okay, and it's an empirical formula estimation only, so it's not always accurate, but in finite element you may need to calculate it out to make it more accurate, your performance analysis. Usually concentrated winding has less end turn because it's shorter. This distribution, this length is actually shorter in concentrated winding. So end turn inductance is usually much smaller in concentrated winding. Okay. So the factor that is the, because when they calculate this end turn inductance, they are ignoring any mutual flux between the two coils that is sitting next to each other, right? So that mutual inductance component can be taken care of by a factor. Again, it's an empirical formula factor. For example, here it is showing what is this factor is for various type of coils. The two coil group we have seen in the previous slide, and for that it was factor Km is 1.68. Okay, plus just be aware that these are all estimation empirical. Okay, and comes from experience only. Yeah, I think that finishes our first part. We are ready for tea break. You will check? Okay, please check, and maybe we'll have a tea break. And please feel free to write your